Now that we've learned about minimum spanning trees, we're now going to learn a couple algorithms for finding minimum spanning trees. So first we're going to review what minimum spanning trees are, then we're going to introduce and describe both of our algorithms. The first one is Kruskal's algorithm, the second one is Prim's algorithm, and for each of those algorithms we're going to work out an example. So remember that a weighted graph is just a regular graph, except we take each edge of the graph and label it with a real number. And if you have a weighted graph, a spanning tree of that graph is a subgraph of that is both a tree and that includes all vertices of the graph. And a minimum spanning tree is, first of all, a spanning tree, but it also has minimum weight among all the possible spanning trees of that graph. So for our first algorithm, called Kruskal's algorithm, it is what I would call a globally greedy algorithm. And what we do is we look at all the new edges available at each step and choose the one that has the lowest weight possible. So if G is a graph, here's an informal description of how the algorithm works. So you just begin with a graph and ignore all the edges, but look at all the vertices of G. At each step, we're going to add an edge to the graph that's going to become an edge in our minimum spanning tree that has lowest weight that will not create a cycle among the current edges in the spanning tree. And then we keep repeating that process until we get a spanning tree. And then that spanning tree, it turns out, is a minimum spanning tree. So if we want a more formal description of what that algorithm is, at each step of the graph, we're going to have a spanning forest. And what I mean by spanning forest is that it is a forest that includes all vertices of the graph. So initially, our spanning forest is not going to be very interesting. It's just going to be all the individual vertices of the graph. So it's all the vertices, but no edges. So a spanning forest in the least interesting way. At each step, we're going to add an edge to our spanning forest that satisfies three properties. First of all, it's got, of course, has to be an edge that we haven't used yet because we want to contribute to getting closer to a minimum spanning tree. Secondly, it has to include vertices in different trees in our forest. So if you look at all the trees in our forest, we're just taking two of those trees, two vertices, a vertex in each of those trees, and including an edge that includes both of those vertices. And then among all those, we're going to choose the one that has minimum weight with those two restrictions. And then we keep continuing until our spanning forest is a spanning tree. And as it turns out, that resulting spanning tree will be a minimum spanning tree. Now, I just want to note that we do end up with a spanning tree in the end. And that is because whenever we have a spanning forest, if we add an edge between two trees, we take those two trees and combine them into one tree. Which means that at each step of the algorithm, that's going to reduce the number of trees in our spanning forest by 1. So we start off with as many trees as we have vertices. At each step, we have one fewer tree in our spanning forest, which means that if we have n vertices in the graph, after n minus 1 steps, we will have just one tree, and that will be a spanning tree. All right, so let's go ahead and apply this algorithm to an example weighted graph. So here's our weighted graph. It's connected, so it has a spanning tree. And we look for the edges that have the lowest possible weight, and that's A to D and C to E. Those both have weight 5. If we look up above that, 6 is the lowest that we have after that. If we add that one between D and F, that will also not create a cycle, so we can add that one. That's appropriate. We have two edges that have weight 7 between A and B and between B and E. If we add those, we still have no cycles, and so those get contributed to our spanning tree as well. Now we have two edges that have weight 8, that's our next lowest weight, but if we add either of those between B and C or between E and F, we're going to create a cycle, right? B, C, E would be a cycle, and E, F, D, A, B, and back to E, that would also be a cycle. So we skip those and then go to the next lowest weight, and that is going to be we have two edges of weight 9. Now we don't want to have B to D because that one would make a cycle, a 3 cycle, but we can add the one between E and G, and now that we've added that edge, that gives us a spanning tree, and as I noted, that is a minimum spanning tree. If you want to add up the weights, you get 39, and that is the lowest possible total weight that we can get from a spanning tree. Okay, so let's go ahead and move on to Prim's algorithm. Now, remember that Kruskal's algorithm was kind of a globally greedy algorithm, which means we looked all over the graph for low weight edges. Prim's algorithm is what I would call a locally greedy algorithm, in that you look very locally, not globally, not at the entire graph, but only locally from the vertices and edges that you have for new edges. So we're going to start with one vertex and just always choose the lowest weight edges that connect to the tree that we've already constructed, not throughout the entire graph. So if G is a graph, what's going to happen is each step in our algorithm is no longer going to create a spanning forest. We're just looking at a subgraph of G that is a tree. So we're not looking at the entire graph. We're looking very, very small, especially at the beginning. So our initial tree is not very interesting. It's just a single vertex that we can choose at random or whatever one looks good to us. It's just any single vertex, and then we don't include any of the edges coming out of that vertex. So what we're going to do at each step is we're going to add both a vertex and an edge to our tree. So this is a little bit different. Before we just added edges because we didn't have to worry about getting new vertices. But since we're only starting with one vertex, not only do we have to add edges to our spanning tree, but we also have to add vertices. And we're going to do it in the following way. One of the vertices has to be not yet part of our tree, right? We always want to add new vertices to expand to a minimum spanning tree. So at least one of those vertices has to be not part of our tree. And the edge that vertex has to be, edge that we add from that vertex has to be adjacent to a vertex that is currently in our tree. So we have a vertex in our tree. Currently, we have a vertex not yet part of our tree, and that's where we're going to get that edge. The edge that we add to our tree that's a subgraph is going to come from the new vertex and also is our adjacent vertex on that tree. And of course, we're going to choose the one of those that has the lowest possible weight. And then we're going to keep continuing until the tree includes all vertices, which of course we're going to do. We always add an edge and a vertex each time, so we keep on going until we get to all the vertices. And the resulting spanning tree will be a minimum spanning tree once again. All right, so let's see what we've got here. So like I said, now we don't have to go for the most globally lowest weight edges. So we don't have to start with those edges that have weight 5. So I'm just going to choose a random vertex. I like the letter G, so I'm going to start with that one. And so our first subgraph that is a tree is just going to be G and no vertices. Now the only vertex I have to look at is G, so the first edge is going to come out of G, which means it's either going to be that edge of weight 9 or that edge of weight 11. And we're going to choose the cheapest one, which is the one of weight 9. That includes the edge with weight 9 plus the vertex E. So we've added a vertex E and the edge between E and G. Well, now in my little tree, I have 2 vertices and 1 edge. And so now I'm going to look at all the edges that come out of E and G that I haven't used and that connect to new vertices. So if I look at between G and E and F, I have edges of weight 11 and 8. If I look between E and D, I have 15. E and B, I have 7. E and C, I have 5. Those are all the edges that I'm looking at, right? Those are all the new edges and vertices that I can choose. And from among those, I choose the one that has the smallest number, 11, 8, 15, 7, 5. 5 looks like the smallest weight, and so I'm going to add that edge between C and E, and then I'm also going to add the vertex C because that's part of the edge. Now I have 3 vertices in my little tree, and so I'm going to look at all the new vertices that are adjacent to those vertices that have edges that I haven't used yet. So I have edges of weight 11. I'm going from bottom to top. 11, 8, 15, 7, and 8. It looks like 7 is the smallest weight that I have, so I'm going to add the edge between B and E. Now I have 4 vertices, and once again I'm going to look to see what edges between those vertices and new vertices that I have. I have edges going from bottom to top of weight 11, 8, 15, 9, and 7. The one that has the smallest weight is that one of weight 7, so I'm going to add the vertex A and the edge between A and B. Same thing now. My new edges and new vertices are going to be either weight, again, going from bottom to top, 11, 8, 15, 9, or 5. 5 has the lowest weight, so I add in the vertex D and the edge between A and D. And now I only have one vertex to add to my spanning tree, and the 3 edges that I can use to get there have weight 11, 8, and 6. It looks like 6 is the lowest, so between D and F, I add that edge. And there I get a spanning tree. Once again, the total weight is 39. So now that you've seen these algorithms in action, you can go ahead and look at the PDF file that's included with this video. It's called Minimum Spanning Trees.